We got a call from a new client requesting a second opinion on this two-stage Goodman gas furnace. On a Sunday after church, we went out, took a look at the furnace. She told us before we went out there that she had a cracked heat exchanger and that the other company said she needed a new heat exchanger. I'm going to go through and check everything on this furnace to provide her with the best option that I recommend based on the condition of the system. So I'm checking the blower wheel now. It's clean. It's not terribly dirty or anything. I spin the blower wheel, make sure that it's spinning freely and we don't have like a seized motor. We'll also check an amp draw on the motor with it running. So we get the furnace up running and everything seemed to sound normal for the most part. We're in the single stage, but you see here, he jumped out the flame rollout switches. So a technician, owner of a company, in fact, went out, he jumped out the flame rollouts and he jumped out the pressure switch up above, which typically when you see something like that, it means they didn't really know what they were doing and they're just trying to jump things out to try to get the furnace to run. They also jumped out the condensate pressure switch because I believe that they were checking the hose to make sure it wasn't filled with water or something, and they put the hose on the wrong port of the pressure switch. So when I went in there, I put the hose on the right side of the pressure switch and it allowed the furnace to pull in enough draft to where it was actually pulling in that pressure switch because they had it on like the positive side of the two ports on this pressure switch. And that allowed the furnace to run without having anything jumped out. But this is how I found it on a Sunday morning. And I was just like, what is going on here? So next what I'm going to do is, because she mentioned something about cracked heat exchanger, I'm going to run it. I'm going to see what it does in second stage. She said in second stage it gets noisier. As soon as it got into second stage heating, you could see the burner on the far right had a definite disturbance, a loud noise. So we're going to get the inspection camera and take a look inside. Now we're going to take my camera, we're going inside of the furnace. We're going to go inspect the heat exchanger with my camera so I can record this, so I can make sure that there isn't a crack in the heat exchanger. I see a huge crack on the far right heat exchanger there, on the cell there. And that's where the air was coming down from the blower motor and pushing air in there against that flame in there, causing the flame to roll out and causing that disturbance that we saw there. So this is important. We check this even on a maintenance, on all of our repairs, just to give our clients peace of mind that their system's working safely.
Oh, wow.
You see that?
Yeah.
Like that, you can't let it run if that's... So now we need to figure out, like, what caused this? Was there something that caused this heat exchanger to fail? And I'm also going to check for CO in the airstream and in the home with my CO monitor on my combustion analyzer. So we're going to put a probe, drill a hole, put a probe here in the supply right underneath the heat exchanger to check the airstream to see if there's any CO actually leaving that heat exchanger. So here I'm just double checking this gas valve. I want to make sure that it's the correct two-stage gas valve for this two-stage furnace. I checked the part number. It is a Goodman gas valve, so everything checked out there. Now I'm going to check the control board just to make sure that there is two speed taps for the airflow in first stage heating and second stage heating to make sure that it's moving enough air, because if it wasn't moving enough air, they had the airflow set too low, we could have a premature failure of a heat exchanger. This is the model and serial number of the furnace. The 14 in the serial number tells us that this is a 2014 model. This Goodman furnace is a GCH950703BXAD model. Here you can see I was actually picking up a low level of carbon monoxide in the airstream of the furnace. Even though it's a very low level, it's still a risk, and because of that risk and other factors, for example, the heat exchanger could crack even bigger and release more carbon monoxide into the airstream. I advised the client to not run the furnace, and I did turn the gas off to the furnace and explain to them what was going on. I'm just being extra thorough and also checking that a vent inside the home, the closest vent to the furnace. Then I'm going to walk through the house, and I also checked through the house, my CO detector, to see if we were picking up any actual CO like in the home. CO detectors in homes, every single one that I've seen so far, they go off at 70 parts per million at 1 hour exposure. The low-level CO detectors go off at 25 parts per million at 1 minute exposure. That's what we recommend and we can bring out for you and set up. Now I'm going to turn on my manometers, hook them up to the furnace. I'm going to tee in with pressure tubing to the pressure switch that was jumped out just to see and confirm that we're getting enough draft. There's nothing maybe weird going on, like with the inducer not producing enough draft, and that way just to be extra thorough to make sure there's nothing else going on here that maybe was causing the furnace to overheat. I'm also going to hook up my manometer to the outlet of the gas valve to make sure the gas pressure isn't too high, which could also cause the furnace to run too hot and potentially crack a heat exchanger. This is my T-brass fitting that I hook up an extra piece of hose to run to my manometer. That way I can tee right into the pressure switch and the tubing that goes to the collector box to see how much draft is being produced here. Now I will zero my manometer before hooking the hose up. Hit 0 on the manometer itself and then click 0 on the app to zero out to atmosphere. Once we get our probes zeroed and we get them mapped, set in the app that this probe here goes to the pressure switch, the other probe down below there will go to the gas valve, then we can get all the data, all the measurements of what's going on with the furnace to see if there's anything that's abnormal, pointing us in a direction of what caused this heat exchanger to fail for the second time. Because we gotta diagnose the root issue, not just throw parts at a system, but go through it thoroughly and do it right the first time. This is an extra step we take. I've seen this skipped a lot before, but a lot of good technicians will check this, and in fact we really need to check this to make sure that the gas pressure wasn't maybe too high, causing the heat exchanger to run too hot, which then caused the heat exchanger to fail and crack. So we're gonna remove this outlet screw, hook up our manometer, check the gas pressure on the outlet side of the gas valve to see if the gas valve is set correctly in second stage and in first stage heating. Currently, I am tightening down this threaded brass fitting inside of the outlet port on the gas valve. That way I can hook up my hose to the gas valve here into my manometer. We can get live readings of how this furnace is actually performing, and then we can see if the gas valve is actually opening, and in this case we know that the gas valve is opening as we got gas, it's running, but make sure the gas pressure is within range to see how exactly this system is performing. Now I'm turning the gas valve back on. Since I had this gas off, the system has not been running because I advised the client to not run the furnace, and we are back on another day to go through the system, check the gas pressure, check the static pressure, check the duct sizing of all the duct work on the supply side where the air blows out, and on the return side where the air pulls in, just to make sure we offer them the best solution for this situation. Because if the gas pressure was really high, then we could lean towards that the gas pressure was the issue. It was set too high from the factory or by a technician and caused premature failure of the heat exchanger. And if we see an issue with the airflow or the duct sizing being too small and we see like a very clear issue, well then we can't just replace the heat exchanger or we'll be back in this situation again. I'm starting the furnace up now. We will monitor the gas pressure, and I'm also checking the draft there, teed into the pressure switch up above and the collector box to see if there's any red flags, and just to check to make sure the draft's good, because the other technician had jumped this pressure switch out. Well, when I moved the hose to the negative port, it's been working fine. So I just wanted to be extra thorough to check that to see if there was anything else going on with the furnace that I wasn't aware of, because if we need to replace that pressure switch, if we were going to do the heat exchanger, then I want to address the full system, make sure pressure switches are working right, everything. So this is the low stage gas pressure. You can see at 1.92. That's right at about the nominal of what the nameplate says for in low stage. You see our draft there at the top where I was teed into the pressure switch. So I'm just going through, I'm looking at everything, and right now you can really see a flame disturbance on that burner on the far right. So what we're doing is just going through the entire system, and checking everything, slowing down, taking our time to do it right the first time, see what we have, and then we'll go from there to make a decision on what we would think is the best option for our client, give them our recommendations so I can provide the client with the best option for repair or replacement. The answers are in the manual, so we always try to be extra thorough, double check the manual, make sure things were installed correctly. And so this is another important step that we take to make sure that everything was set up properly. We're also going to check the gas pressure to see what it's supposed to be set to in low fire and in high fire. So in first stage and in second stage, we're going to check in the manual to see what the gas pressure is supposed to be set to make sure it was set correctly. For some context, the heat exchanger on this furnace was replaced 7 years ago. I can't tell you how many times I've seen just a furnace not installed correctly, didn't have the right forward slope to drain the water in a condensing furnace, the drain line wasn't done right, so many different scenarios. But for some context, the heat exchanger on this furnace was replaced 7 years ago. So before I even think about just offering to replace a heat exchanger, I need to see what's going on with this entire system. Here we can see that the gas pressure in low stage should be 1.7 to 2.3 inches water column, which is 2.0 nominal in the middle there, and high stage is 3.2 to 3.8 inches water column, 3.5 being the nominal in the middle of that range. And that's what our gas pressure was set to. We'll see that here in a second on the MeasureQuit Bluetooth app of our live readings that we took. So we've confirmed that the gas pressure wasn't set like extremely high or anything, causing it to run too hot. We also confirmed that the orifices in the furnace there for each burner are sized correctly. Sometimes if it's a higher altitude, certain setups, you do have to derate those by installing smaller burner orifices, because at higher altitudes the air is less dense, meaning there's less oxygen available for combustion. This is what our outlet gas pressure is in second stage heating. It's 3.44, which the nominal is 3.5. That's the middle of the 3.2 to 3.8 range. So that's within spec. Ultimately, you would want to do a combustion analysis, clock the gas meter to determine the exact gas pressure that you should set it to make sure everything's burning efficiently and safely. The supply air is the air that's leaving the vents, coming out of the vents. The warm air right now in heating mode. The return air is the air that's returning through the furnace, pulling in on the return. So our temperature rise in second stage on this furnace would start climbing very quickly toward the 65 degree max temp, and this would then trip the high limit. And so what I determined is, even with this setup, when we're running it, it doesn't even run in second stage for more than 10 minutes before tripping the high limit. And we confirmed that the issue is that it's not moving enough air, and it's overheating the heat exchanger and the furnace and tripping the high limit. So next what we're going to do is we're going to go through, check the ductwork, see if there's any restrictions, see if everything is sized properly, or at least close to what it needs to be sized to move enough air for this 70,000 BTU two-stage gas furnace. We sped this live data reading up, but it took about 5 minutes in second stage heating, and then it would trip the high limit on the furnace, which is a safety that basically turns off the gas valve. It keeps running the inducer to keep the fumes moving and keep it cool, and it only runs the blower motor. So at this point, when it gets close to 63 degrees, which is close to the max, the high limit turns off the furnace and only runs the blower motor, cools down, and it starts over. The furnace will run, overheat eventually, cool down. And this short cycling with the heat exchanger heating up, cooling down, more frequently cause the heat exchanger to crack sooner than it should. Now I'm drilling a hole so I can put my static pressure probe right above the coil to get the airflow reading here to see basically what the balloon force is in there, what's the resistance of the ductwork, how smooth is the air moving here, is there a restriction on this coil, and that's something we also look at with our camera, make sure the coil's clean. So this just tells us if we're moving enough air and where our issue may be. If it's very high on the supply side, then we know our issue would be down below somewhere on this end. If it's very high on the return side, we know that an issue could be up on that side as well. Now I'm putting the threaded cap back onto the outlet port of the gas valve, tightening that down. Now that we're done testing it, we'll tighten this back down, make sure everything's sealed up. Then what we're going to do is drill our holes for our static pressure probe right above the coil. I'll set my manometer here, get everything set and ready, and we'll check our static pressure across the coil. We'll check our static pressure across the filter. We'll check our static pressure after the filter. Basically, multiple measurements we take to get a full static pressure screening. The balloon force, basically inside the air exerting on the ducts inside, from the inside pushing outwardly. And this will get us the basically blood pressure of the airflow system. How well is the air moving? Now I'm going to drill one of my holes to get the static pressure probe in there with a special bit that actually stops as soon as it drills a hole, so you don't have to worry as much about hitting something on the other side. Although the heat exchangers sit so far back, but for a coil, for something like that, we are extra cautious. We know our equipment, and so we know where to drill to make sure nothing is damaged. To be extra safe and cautious, we use that special bit that doesn't drill all the way through, made by the Energy Conservatory. So I checked my static pressure there above the filter and after filter. I got the filter pressure drop, but we did then check, like you're normally supposed to, after the filter and before the coil to get our total external static pressure. Now we're going to look at the total external static pressure of this system. Basically, it's the balloon force exerted outwardly inside the ducts. It's the blood pressure of the airflow in the HVAC system. The nameplate says the max rated total external static pressure should be 0.5. A lot of the times I see it higher than 0.5, but ideally the pressure drop across the filter, the coil, the duct design system should equal up to 0.5. This is our pressure drop across the coil, above it and below it, giving us 0.20, which is normal, that's in range. This is above the filter, and below the filter, our filter drop would be 0.16, that's within range. This is an extra step we take to make sure that the airflow across these components is within spec. That way we can provide the client with the best option to resolve the airflow issue that they're having that's causing these heat exchangers to crack. Now we're going to check what the amp draw is on the blower motor with it running and with the door on to see if the amp draw is running really high or anything like that, just to be extra thorough to make sure there isn't an issue with this blower motor that could be causing this furnace to overheat. After thoroughly going through the entire system, we also found out from the client that this would be the third heat exchanger getting replaced. So another company replaced this furnace that was here before. It was a York furnace with this Goodman furnace, 70,000 BTU two-stage furnace. And at some point the heat exchanger failed. She has receipts of this. And then fast forward 7 years later till today when I was out diagnosing, this would be the second heat exchanger that's failed on this furnace since it was installed. Another company said they were going to come back with the heat exchanger. She canceled with them once I went through the entire system. I said, look, even when it's running, it's overheating and not working right. You should not have had 2 heat exchangers fail within that amount of time and have another failed heat exchanger. After going through the entire system thoroughly, what we determined is the ductwork is just too small for the air conditioner and for the furnace. They have 1.5 ton ductwork on a 2.5 ton air conditioning system. And so the 14-inch pipe return is too small and the 14-inch supply pipe in the crawl space is too small. It can produce maybe 750 CFM. We need more like a 16-inch round pipe to be able to get the design airflow of around 1200, which will then, with the higher static, would have us right to where we'd want to be, closer to that 1000 CFM mark. If we upsize the ductwork and modify the ductwork, the new heat exchanger would work, but the client did not want to spend the money on the ductwork. We had another solution that we offered the client with downsizing to a 60,000 BTU modulating variable speed Daikin furnace that comes with a 12-year part warranty, a 1-year labor warranty through St. Tony's Heating and Cooling, and a 12-year unit replacement warranty where if the heat exchange or something major like that failed, they'd give you a brand new furnace one time within those 12 years. This is a perfect example of why diagnosing the root issue matters. If we had simply replaced the heat exchanger without looking deeper into the system, we likely would have ended up with another failed heat exchanger down the road, Just like with a doctor, if you don't diagnose the root problem, you're only treating symptoms. That's why at St. Tony's Heating and Cooling, we focus on thorough diagnostics, quality work done right the first time, and clear communication throughout the process. In the next video, we'll show the new furnace installation and the solution we put in place to fix the problem properly. Restoring comfort and peace of mind, one job at a time. And until next time, blessings.